Hello class, how are you guys doing? It's Miss Sandra here again. And as we said the last time, I said I was going to go through my slides to help you guys go through what we read or what we did in class. And I know some of you did not have time. And some people were sitting at the back, you couldn't really listen. Then in our second class where I talked about the graph, the growth, the log phase, lag phase, stationary phase. Some students were not able to attend because of the clashing timetable. And we had some calculations that we did there. So we're going to be going through it to help everyone be on the same page. So I know you guys have your slides with you. So I'll be going through my slides and I'll be doing some explanations. If you have any questions, do well to go to the comment section of this video and ask your questions before the semester exam and also before the main exam. So back to our slide. We talked about the requirements, the growth requirements for different microorganisms. We focused on temperature, pH, that's pH, we're talking about acidity and basic alkaline. Then we also talked about carbon source. Then we talked about the growth phases, that's, and we also talked about oxygen requirements. So the last time, most people did not understand oxygen requirement because I guess my voice was not that loud. So we talked about aerobes. We have aerobes. These are organisms that love oxygen. They thrive in oxygen and filled environments. Then we have microaerobes. Microaerophiles are organisms that require a little amount of oxygen to thrive. Then we have anaerobes. Anaerobes are organisms that do not require oxygen at all to thrive. But we also have obligate aerobes. These organisms, they just cannot do without oxygen. In the case of an aerobe in an environment that does not really have oxygen, it will probably survive for a few minutes. But for an obligate aerobe, it's going to die immediately. It really needs oxygen to thrive. But we have facultative organisms. Facultative organisms are organisms that thrive whether in an aerobic or anaerobic environment. They've conditioned their system to thrive even in the presence or in the absence of oxygen. Then we have anaerobes. These organisms do not require oxygen to thrive. They usually grow well in an anaerobic, that's oxygen deprived environments. Talking about anaerobes, we have aerotolerant anaerobes. These organisms, they can actually thrive. They don't really need oxygen to thrive. But in the presence of oxygen, they wouldn't really die, but they don't actually make use of it. They just coexist with this oxygen, but they actually make use of they do not make use of oxygen to survive. So they're in the presence of in an oxygen-based environment. They are present there. They don't really need the oxygen, but they are able to thrive. They are able to make use of CO2, other sources of um they make use of other sources, not oxygen, but they actually thrive in the presence of oxygen. If you're a little bit confused about this, you can ask me your questions and I'll try to clear it up later. Then we have obligate anaerobes. These organisms are killed by oxygen. Obligate anaerobes. That means they're obligated to thrive in an environment that does not require oxygen. Do you understand? And if you go to your next slide, you would see where I listed out all these microorganisms because we really cannot do without their examples. For aerobes, we have Nacodia, Pseudomonas aeruginosa. From the name already, you know that this organism actually requires oxygen. This particular organism needs oxygen to thrive. We have E. coli, Salmonella, Klebsiella. There are plenty. You can make your research. Then we have microaerophiles. These organisms require a little amount of oxygen to thrive. You have Helicobacter pylori, Borrelia, and you can just go through and find other examples. Then we have aerotolerant anaerobes. These organisms do not require oxygen to thrive, but they are able to tolerate it at a little extent. They're not going to die. They coexist with this oxygen, but not that they require it to thrive. So for the examples, we have lactobacillus, we have streptococcus pyogenes. Then we have microaerophiles, as I told you. They require a little amount of oxygen, and I've told you, but I've mentioned the example before. Okay, so now I'm going to pH requirements. pH requirements. We know that the neutral pH is 7. So anything above 7, from 6 to 1, we are talking about an acidic environment. And from 7 to 11, 14, we're talking about an alkaline or a basic environment. So there are organisms that only thrive in acidic environments. These organisms are called acidophiles. They love any pH that is less than 3, they thrive very well in it. We also have moderate acidophiles that go in the range of 3 to 5. Then we have alkaliphiles. These organisms thrive well in a basic environment. They grow in the range of 8 to 10.5. Then we have neutrophiles. These organisms thrive in pH range of 6.5 to 7. Do you understand what I'm saying? Yeah. So we have different examples for this. We have extreme acidophiles. You'll be seeing these organisms from 1 to 3. We have acidanus, we have metallosphera, we have pyrococcus, and we have moderate acidophile. I'm just mentioning the examples to you. You can go through your slide. What I basically need you guys to understand is the meaning of these terms. Then you find examples of these organisms that you can associate with them. Do you understand? We have alkalifiers. These organisms love an alkaline environment, a basic environment. A particular example is Bacillus subtilis. This organism thrives well in an alkaline environment. You can go through your slide for other examples. Okay, now we're going to carbon source. Now, for human beings, for us to live and coexist, we need something that is going to give us energy. And for microorganisms, they have organisms that require they obtain their carbon source from organic materials like rocks. They can break down some organic materials and obtain carbon from it. But we also have, and this particular group of organisms are called chemotrophs. But we also have some organisms that can be able to generate their carbon source from CO2. And these organisms are called autotrophs. Example of these organisms are the purple sulfur bacteria, the purple non-sulfur bacteria, and so many others. This particular group of organisms are able to fix carbon from CO2 that is found in the environment and turn it, they turn this inorganic form of carbon into an organic molecule and make use of it. So these particular organisms are very unique in their ability to fix carbon from the environment, from CO2, and turn it into an organic form that they can make use of. And they are called autotrophs. While chemotrophs behave like most human beings that derive their carbon sources from the environment, like from carbon, like you can get there are some particular organisms that get their carbon source from rocks. They break down organic substances to obtain their carbon source. And we have these examples. I think I mentioned some examples. Okay, I asked you guys to find out the chemoheterotrophs. Then I also give you guys some example on the autotrophs. Okay, now we're going down to the bacteria population growth. I know so many of you were not able to attend the class, so that was why I decided to make this video in particular. Because I know in our first class, the one I went through, almost everybody was there. I'm not sure I talked about temperature because I know I actually took my time to explain it. But just let's do a little recap. We have cycrophiles. These are organisms that thrive in cold environments. They grow basically in a temperature of minus 20 to 10 degrees centigrade. They grow in glaciers, polar regions, north poles. These are where you find these organisms. And you have some of the examples. I give you the examples on your slide. You can go through them. Then we have the mesophiles, these particular organisms. In our class, you can remember we call them the warm bodies. These organisms thrive in human temperature. And these are particular organisms that usually affect us. These are the organisms that are pathogenic to us. They cause disease to us because they grow in the same temperature with us as human beings. You're finding them in the range of 20 to 45 degrees. And you know that the human temperature is 36 degrees. That is why they thrive so well in it. So you can, from the top of your head, you can mention E. coli, a particular organism that you know usually causes human diseases. So E. coli is a mesophile because it thrives in this range of temperature. And other organisms, most pathogenic organisms that cause disease to human beings are mesophiles because they grow in the same temperature with us. Okay, I also decided to break it down into two groups for you guys. We have room temperature mesophiles. These organisms grow in the range of 20 to 35 degrees. We also have body temperature mesophiles. These organisms are found in warm-blooded animals and they have a mutualistic relationship with us and they are usually our normal flora. These are the organisms I was telling you guys about, like E. coli, like yeah, like you know in the human, female human, in females, actually females thrive like our reproductive organ. Like most times we have all these organisms because of the nature of that place, and it creates a conducive environment for these organisms to thrive. And usually our body have this temperature range of 35 to 45. That's the temperature range, and this is why these organisms begin to thrive in this environment. It's not like they are hitting on you. It's just that your body provides an excellent environment for these organisms to thrive. Okay, so next, I just wanted to touch on that before we go down to our bacteria population growth. So in the last class, I was telling the microbiologists in class, I know some of you were not able to attend, that bacteria, we do not measure the growth of a bacteria like the growth of a human being. When as a baby, as you're growing up, when you eat food, you add in size. When you see a healthy baby, the baby is all chubby according to your definition, but that's not really the definition of a healthy child. It's when the child everything is working, all his organs is in good. Size does not really determine the health of a human being, but most times that's what we use to measure the health of a human being. But unlike human beings, organisms their growth is not measured in size. We measure their growth by numbers. You cannot measure the growth of a particular bacteria that it's adding weight, is growing in size. We measure their growth by binary fission, by the ability to multiply, one cell breaking down into two cells breaking down into four cells. This is called binary fission. This particular um these organisms are called prokaryotes. Prokaryotes, they are single celled, so you cannot measure their growth by the increase in size. You measure their growth by the doubling of their cells because they are single celled organisms, unlike human beings that we have multiple cells in our body. Do you understand me? So that is how we measure the growth of a bacteria. We measure their growth not in cell increase but in cell number by multiplication of their cells. And next thing we're going to be talking about is generation time. This is actually the time taken that is required for a particular organism like a bacteria to double in size to produce two daughter cells. Then we also have what is called the growth curve. The growth curve is a pictorial picture of a graph that helps us understand the phases that a particular organism that is being isolated or inoculated into a media takes. Like, when you're trying to write somebody's biography, you're writing from the time of birth to death. The growth curve is like a biography about an organism that is telling you how this organism lives its life out from the time you inoculate it into a petri dish to when it's going to die. So, and this growth curve, we have the log phase, we have the lag phase, exponential phase, we have the stationary phase, and we have the death phase. And that's what I'm going to be talking about in a minute. So let's go straight up to it. If you're going through your slide, I'm in slide 17 right now. You can see where I explained all these phases, but let me just use the graph to bring the story home. So a lag phase, what actually happens here? The organisms, these bacterial cells are just inoculated into a new fresh medium. They are trying to get acquainted with the environment. They are beginning to synthesize enzymes, proteins that will help them begin to break down the nutrients that are provided for them. So at this point, there is no growth. It's just like when you moved into a new environment. You're still trying to get a new house. You begin to clean up the place. You're trying to get acquainted. You begin to check the room. You check the parlor. You check the room. You've not even started living. You've not started growing. You're just there. You're trying to get acquainted. You begin to clean up your house. This is what's happening to these organisms at lag phase. They are trying to get acquainted to the environment that they just arrived. And they are also trying to recuperate from some injuries that might have occurred on them while they were being inoculated with a loop. You're moving them from one habitat to another. You're isolating the organism. So it's trying to get acquainted. And the process of isolation, you'd have even injured them. So they are trying to like recuperate and get well before they can actually begin to understand what's happening in the environment. So this is what happens at lag phase. So after the lag phase, now we move to log or exponential phase. This is where the growth process begins. This is where that's breaking down. One cell becomes two cell becomes four. At this stage, the organism is making use of all the nutrients that is provided in the medium. It's breaking down the nutrients. It's metabolizing. It's making use of the nutrient that is provided for it. At this point, you can just say the organism is living the best time of its life. Like, it's everything it needs is provided at the right temperature, at the right pH. This organism is going to thrive at exponential phase. At this phase, this is where growth occurs generally. Then after that phase, you can see that it has a slanted. It increases in a, like, it's a slant that goes up so quickly. Then you come to a leveled ground that, like, a what do we call it, a horizontal platform that is called the stationary phase. Now at stationary phase, what happens here? The nutrients are beginning to reduce. So um the amount of production, let's say if we have two cells that are being produced, it's equaling to the amount of organisms that are dying. Nutrients are beginning to run out. They've already produced in large number. At this point now, growth is equal to death rate. Like, they're growing at the growth rate and death rates become level. These organisms are running out of nutrients. Some studies also showed that at this point, they begin in a bid to survive. They are trying to outgrow others. They're beginning to compete for food. The food is no longer enough. Some organisms produce antibiotics that would help eliminate other organisms. So at this point, most time, this is where we isolate these antibiotics at this phase. At this phase, these organisms, they begin to produce antibiotics that would help them thrive more and kill off their fellow cells. Do you understand? So that's what actually happens here. There's exhaustion of available nutrients. There's accumulation of inhibitory metabolites. There is exhaustion of space. There is no space anymore. Do you understand at this point? And they also said at this point too, some organisms begin to produce spores. But this can also happen at stationary and also the death phase. Spore formation is the ability of an organism. When organisms begin to produce spores, they are trying to save themselves from an uncomfortable environment. So, and this at stationary phase, the organism is beginning to become uncomfortable. Nutrients are no longer enough. They are trying to thrive. They don't really want to die. So they are trying to do everything that will make them exist, make them live more, make them survive. So they begin to produce spores that will help them live more. And from there, we are going to the death phase. At death phase now, if the viable cell growth begins to decline, you barely see cells doubling. You're now seeing that most of the cells are dying. There's no more nutrients. Here, spore formation is mostly experienced at this point. You begin to see turbidity. If you're growing the organism like in a, what do I call it now? Should I say conical flax, or you're growing it in a tube, you would see there is turbidity in the tube. Like, you see that there is more growth, there is a decline. The organisms are beginning to die at this point. It's actually the reverse of log phase. At log phase, there is exponential growth, but at death phase, the organisms are beginning to die. Okay, so you can see where I explained it at slide 20 with a graph, the lag phase, the log phase, the stationary phase, and the death phase. Then the horizontal part of this graph is showing you the time it takes, and it's usually in hours. Then you have the vertical part is telling you the number of bacteria. Okay, so I would also want us to, in our class, we try to calculate the generation time. And I told you that the generation time is the time it takes for this organism to double. So we actually calculate this with a formula called, written as G is equals to T over N, where G is the generation time, T is the time, probably in minutes or an hour, depending on the question that you're being asked. If you're asked to calculate in minutes, you know what to do. If you're asked to calculate in hours, you know how to convert it. If you're asked to convert 1 hour to minutes, what does it mean? 1 hour to minutes is what? 60 minutes makes 1 hour, so that's 60 minutes. If you're asked to convert 2 hours to minutes, it's going to be 60 times 2. That's 120 minutes. That way you continue. So you're having G is equals to T over N, where N is number of generation. Most times, the problem we have in this question is how to derive N, but we now have a formula that can help us generate N. So our final formula, if you're looking at your slide, is G is equals to T over 3.3 log. There was a big typo error in this. In class, I tried to explain it. G is equals to T over 3.3 log NO over NT. I'm coming. No, log NT over NO, where NT is your final population of organism and NO is your initial population of bacteria or organism cells you have. So I give an example here. What is generation time of the bacterial population that increases from 10,000 cells to 10 million cells in 4 hours of growth? Now, from this question, you can understand that the NO is what? The initial population you have is 10,000 cells and your NT is 10 million cells. So if you're going to calculate this, we're having that C is equals to, remember they said in 4 hours of growth, and you know that we usually calculate this in minutes. So how many hours? 4 hours is going to be what in minutes? What are you going to do? You're going to do 60 times 4. And if you do 60 times 4, you'll be having 240 minutes. Then your formula is G is equals to T over 3.3 log NT divided by log NO. Right? So if you insert your values here, you'll be having 240 divided by 3.3 log 10 raised to power that's 10 million cells you have. That's your final population. And 10 raised, you have here 10 raised to power 7. Then your 10 raised to power 4 is your initial population time. So if you do everything, you'll be having 240. If you using your calculator, if you press log 10 raised to power 7 divided by 10 raised to power 4, you'll be having 3. When you multiply it by 3.3 and use 240 minutes to divide, you'll be having 24 minutes as your final answer. Make sure and note to always understand your NC, which is your final population of cells, and your NO, which is your initial population of cells. And also remember to convert your time, which is usually in hours, to minutes. So if you're giving 5 hours, you know you're doing 60 times 5. If you're giving 10 hours, you know you're doing 60 times 10, because you're trying to convert your hours to minutes. Okay, I also talked about the growth rate constant. This is quite easy. From our last last formula, if you're able to determine your N, which is your number of generations, then you can actually determine your growth rate constant, because the formula is your growth rate constant is equals to the number of generations divided by time. So in the case of microorganisms, as I wrote here, it's usually expressed as generations per hour. That's from your graph if you're looking. Then there is also a formula here to get that scale. You have log 10 brackets NT minus NO divided by 0.301T. It's just for you to insert your values. From this now, our NT, using our formal question, our NT is 10 million cells, that's 10 raised to power 7. And our NO is 10,000 cells, that's 10 raised to power 4. If you insert these values in this and you press them, punch them on your calculator, you'll be able to get your growth rate constant, right? And that's a summary of everything I taught you guys. So if you have any questions, you can actually come to the comment section of this video and ask me your questions, and I'll be willing to help you guys out. I hope this video was quite educative, and it has helped those that were not in class to help them catch up. If you have any questions, feel free to ask me. I'll be dropping this video on my YouTube, and I'll also be dropping it on my TikTok to help create more awareness. Then I also wanted to mention that if you have any other question on any topic that you're being taught on this particular course, MCD 201, you can also ask me. I'll try to do the research and teach you guys if I have the time. Just ask me. I'll try to do a video. Like if you've gone through a class with a lecturer and you don't really understand what they were saying, I can help you guys. I'll just drop your questions, ask your questions, and I'll do a video on that topic, okay? Thank you guys for listening. Have a wonderful day. Bye.